Hi everyone, and welcome to a quick review of Lesson 8.2's Tests of Symmetry. Let's take a look with this example. So I have r equals cosine 2 theta. Now the first test of symmetry is this one, where you replace theta with negative theta. And that's to tell if it's symmetric across the polar axis. And what that means for us is if we draw the polar axis, which is basically the positive x-axis, then any point that is above the polar axis would be reflected straight down to below the polar axis. Okay, so that's how that works. Let's take a look at what happens in our calculations. What I'm going to do is I'm going to take negative theta and put it in here. So I have cosine of 2 times negative theta. Now 2 times negative theta is negative 2 theta. And remember, the even-odd properties for cosine say that this results in a positive. So this is cosine of 2 theta, using that even-odd property. Okay, so this passes the test because this is the same as my original function. It got the same result. Now, another way you could do it is by picking a test point on your unit circle. I'm going to use an easy one, like pi over 6. So if I do pi over 6 times 2, because this said to do 2 times theta, I'll get pi over 3. So I just have to check if cosine at pi over 3, here, the 1/2, is actually equal to cosine at negative pi over 3 down here. And actually those two cosine values are equal, so it does work. So you can do this using a test point. I prefer using a little bit of algebra. Let's take a look at our next test for symmetry. That's where you replace r with negative r, and that's to see if it's symmetric about the pole. Now, symmetry about the pole means that if I was to draw at pi over 6, whatever point I would have, it would be reflected across in the other direction. So whatever point was up here is going to reflect across the pole. So it's like continuing the straight line that would have been at pi over 6, and it would be on the other side of that line. Okay, so let's see if it passes that test. So I'm going to take my function and replace r with negative r. So this becomes negative r equals cosine of 2 theta. Okay, so what I'm going to do is I'm going to divide to get the r alone. So I get r equals negative cosine 2 theta. Now, negative cosine 2 theta is never going to equal positive cosine 2 theta because it's going to change the sign. And we can check it with our test point. If I use pi over 6, 2 theta is going to be up here, 1/2. And 1/2 and negative 1/2, because that would be negative 2 theta, are not equal. So it doesn't work on that. Okay, so it failed this test. Now, our last test is to replace theta with pi minus theta and see if it's the same. And that will be a reflection across theta equals pi over 2. So that's like our y-axis. Here is theta equals pi over 2. It's a vertical line at pi over 2. And here's my polar axis. And what that would do is anything over here would be reflected across that line. Okay, so that's what would happen with this one. That's what it's going to tell us about. Let's check to see if it works. So I have r equals cosine of 2 times, now it used to be theta, but I'm going to put pi minus theta here. Okay, now this can be simplified. I'll get cosine of 2 pi minus 2 theta. And I need to double check to see what's going on with this one. And this one can be the trickiest one to do. So I would highly recommend doing it using our test point. So let's take a look. Okay, 2 theta we already found is at pi over 3. Pi minus theta times 2, or 2 pi minus 2 theta, is going to be 2 pi minus that pi over 3. It's going to be down here. Okay, so we had pi over 3 was our 2 theta, and then I have 2 pi minus pi over 3 is going to be down here. Notice their cosine values are actually equal. Okay, so it actually does pass this test. So check for test number 3. So I know that this function is symmetric across the polar axis and symmetric across theta equals pi over 2. Now, with any function, it is possible that it is not symmetric across any of these lines, and it's possible that it only fits one of these, or it could fit all of these. So you have to check each and every one for all of your functions. Okay, so that's it for this. Let me know if you have any questions.